If you ask a programmer to write math rules for specific shapes to identify a cat, pointy ears, a long tail, the code will fail the second the cat curls into a ball. The physical world is simply too messy for simple formulas to cover every possibility. To teach a computer to recognize that cat, we have to change our approach. Instead of giving strict instructions, we hand the machine a million pictures of cats and let it figure out the patterns on its own. In traditional programming, you give the computer data and a set of rules, and it calculates the answers. In machine learning, we give the computer the data and the answers, and it calculates the rules. We call this first method supervised learning. Think of it like a teacher holding up flashcards for a student with a clear answer key. We show the computer an email and tell it, "This is safe," then show another and say, "This is spam." By feeding the algorithm millions of labeled emails, it detects hidden patterns. It realizes certain links combined with the time sent mean junk, even without spam words. As scammers change tactics, the system autonomously adjusts filters to catch disguised scams. By learning this way, computers operate less like calculators strictly executing commands, and more like students building intuition through experience. Sometimes we have a mountain of information, but no answer key. It is a bit like giving a child a massive box of mixed, unlabeled toys and asking them to organize the pile. When humans do not have the time or ability to label the correct answers, we rely on unsupervised learning. The algorithm looks at the raw chaos and sorts the data entirely based on hidden similarities. Without knowing what the individual items actually are, it groups them by how close they are to each other. Everyday recommendation algorithms run on this logic. Streaming services group your viewing habits with thousands of other people to predict what you might want to watch next. The machine does not actually know what a movie is. It only sees the spider web of connections between millions of accounts, finding patterns in our choices that would take us lifetimes to sort through by hand. Data isn't always static. When a machine needs to take action, like navigating an interactive space, the environment becomes dynamic. This third method is reinforcement learning. There is no historical data to study and no teacher to provide the answers. The machine learns strictly through trial, error, and consequences. We program the digital agent with a single goal: maximize your score. Over millions of repeated tries, it loses points for failure and gains points for success, slowly figuring out the exact sequence of actions required to win. In 2016, a program called AlphaGo applied this trial and error approach to master the ancient board game Go, facing off against a top human player. The machine didn't study how humans played the game. By rapidly playing millions of matches against itself, it invented new strategies that no person had ever conceived. By trying to get a reward through millions of failures, machines can move past mimicking human knowledge and begin creating their own solutions. These pattern recognition engines are now deployed in high-stakes environments. Medical professionals use them to analyze scans and spot the earliest microscopic signs of disease before a human eye ever could. But because the machine teaches itself, we face a big problem. It is like a black box, a locked room where the computer does the work, but there are no windows for us to look inside and see exactly how it is making its choices. If the training data is flawed, or if the system encounters something it has never seen before, the logic can fail. This happened in 2018 when a self-driving test vehicle failed to stop for a pedestrian. The computer only knows the specific patterns of pixels it was taught. Because it doesn't understand the real-world context of a person walking across a street, it can make a fatal mistake that a human driver would recognize instantly. The student is brilliant, but it is literal. Its output is strictly bound by the exact limits and prejudices of the data we feed it. To push past the limits of simple pattern matching, researchers began to ask a new question. What happens if we try to digitally reconstruct the actual architecture of the human brain? That is the world of the neural network.